So uh, we started this topic the last day, branching. This is the last aspect of Git and version control that I'm going to look at. Where branching becomes really important is when you've got a number of people working on the same repository. Now, admittedly, that would mean we'd have to be using something like GitHub, but we'll actually simulate it the next day in the lab where you'll just be working on your own local repository, but you'll have multiple branches going on at the same time. So that's effectively a good simulation for when you've got multiple people working on a single repository. And so we use branching really every time we're doing any kind of development work. We should be working on a branch that is not the repository's master branch. Eventually, as I said the last day, you will want to merge the work that you're doing onto or into the master branch. But strictly speaking, it's kind of highly recommended that you should never be committing directly onto the master branch, especially if you're working in a team, because the master branch is always considered to be the current working, keyword being working there, the current working version of whatever application you're working on. So if you're in the middle of doing some development work and you've committed, but it's not completed yet, then you don't want other people accessing that work until it is completed. And if you're committing onto the master branch, then they can access it. So essentially, when you're doing any kind of work, whether it be bug fixing, refactoring, development work, experimentation, always do that on a separate branch. And so the workflow then should be this branch edit merge workflow, which we'll see. Physically, what is a branch? So now that we've gone through the lab on Tuesday, we've got a good sense of what a repository looks like internally. It's a whole series of commits where each commit has a snapshot of the working directory at the time you made the commit. Up to now, whenever we did a commit, we were committing on to the master branch. And really all a branch is a simple little file that contains the hash of the last commit that you did to that branch. Okay, so we can visualize it as a pointer to a particular commit object. And up to now, as I said, when we've been committing, we have been committing to the master branch. So we have this simple little file, and I think I showed you on the, well, sorry, before I do that. So when you create any repository, initially it has by default this branch called the master branch, and you'll always know what branch you're on. When you type the git status command, it tells you immediately, as well as telling you what changes you've been making to your working directory. And so when we get to the stage where we'll have multiple branches, this is how Git knows which branch are you committing to. Because if you type git status first, that'll tell you which branch you're on. Now we'll find out in a moment how does Git know which branch you're on, but whichever one it is, when you do a git commit down here, you don't commit to a branch. You cannot do that. You can only just say, I want to commit the work that I'm doing, and it will decide that what you are committing to is the branch that you're currently on. You can change what branch you're currently on. We'll also see how to do that. So I think this is roughly where I got to the last day. Branches they have to be represented some way internally within the Git repository. And we said the last day that if you look inside a folder called the refs folder within your repository, and within that, it has a subfolder called heads. And inside of that folder, there'll be a file for every branch associated with your repository. And of course, by default, there is one there called master. And if we looked inside the contents of that file, just using an ordinary text editor, then we will see something like this on the left. And this is the hash of the last commit that you made to that particular branch. Goes without saying that you've got to be extremely careful, because if you accidentally change any one character on the string, then your repository is corrupted and it's almost impossible to recover that. Not easily anyway. So how do we create our own branches? Here's the command. Git branch and whatever name you want to give to the branch, and it's completely open-ended. It can be hyphenated. Obviously, you can't have spaces, but other than that, it's completely open. What you want to call the branch, you would give it some sensible name, obviously. And what this command does is it simply creates another branch file in that directory that I showed you on the previous slide. The name of the file will be this. Okay, so you will see exact names of branches represented in the repository as files. The content of the new branch file will have the exact same commit hash value as the branch that you're currently on. So let's assume we're currently on the master branch, and it's pointing, the master branch is pointing at a particular commit object. When you submit this command, this new branch now is pointing at the exact same commit object. There's no change to your working directory as a result of this command here. It only makes that simple little additional file to the repository. We can visualize it now like this. We now have two branch files. These are representing branch files in my representation anyway, and both of them are pointing at the exact same commit object. Simple little example again. So I've typed git status. This is the response that I've gotten back. I've then typed this command. The cat command is just a command on Mac. Don't know if there's the equivalent on Windows, whatever the equivalent command is on Windows. All I'm doing here is I'm displaying the contents of the file, and here I'm providing the actual path name of the file. So I'm digging down into inside my Git repository, right down as far as the master file, and I get back that as my response, let's say. Then when I create a branch and I cast the contents of the branch file, it has the exact same commit value. So that confirms that both branches are, as we say, pointing at the exact same commit initially. Note when I do git status, I'm still on the master branch. Now there's this other special file called the head file, and the head file is referring to the particular branch file that you are currently committing to. So it's actually this head file. That's how Git knows what branch you're currently working on. So when you type the git status command, what Git does is it goes looking for this head file, and the head file will contain the path name of the branch that you're currently working on. And then when it has that branch path file name, it then knows it can find the commit object for that branch, etc., etc. So this kind of head file is pivotal to the whole working with branches inside in Git. So it's a special Git pointer file. It's always pointing at, as we call it, the current branch. The current branch is the one that you're committing to. The current branch is also the one that is kind of aligned with your working directory. So we can now visualize it like this. Here's my head file. It doesn't contain a hash now. It just contains the path name of the particular branch, one of the branch files. So right now I'm assuming that the head file contains the path name of your master branch file. And so this connection here is what allows Git to know what is the current branch that the person is committing to. So a little sequence, I do git status, tells me this, then I use this cat command again, whatever the equivalent is, and I actually cat the contents of a file inside in the base folder of the Git repository itself, or in the root folder of the Git repository. And the file is just called head. If we just flip over to simple little repo that we have from last week. So if I dig down into this one, there you can see the head file there, and I can actually just view it using an ordinary text editor, and that's what it contains. Okay, so that's just the path name of a particular branch file, as I said. So git status, then I cat the contents of the head file for this particular scenario. It's giving me that, and that's just confirming what I just illustrated to you. Let's follow a simple scenario. So what I'm showing you here is, let's supposing this is the status of a repo that I have. So the way you kind of interpret this now, C here represents a commit object, let's say. Now we know that behind or underneath that commit object, there is a whole network of blob and tree objects. That's our understanding. We don't have to show that kind of detail anymore. So it looks like I've done 3 commits, and my master branch file is pointing at this commit and head is pointing at master. So that's my current repository situation. And we're saying, supposing we do some we want to do some experimental work and commit that experimental work, but we don't want to affect the master branch with this experimental work. So our solution is create a new branch. So I do that. I create a new branch, and I'll expand on this git checkout in a moment. But if the effect of the git checkout command is to switch to this branch and make this branch the current branch. So let's supposing I've done that. Then I do some development work in my working directory as normal, and I stage and commit that work. So now I can visualize my repository like this. Here's the new commit. Master is still pointing at what it was pointing at. My experiment branch file is pointing at the new commit, and head is pointing at experiment. This connection here happened as a result of this line here. So, and I might do some more commits along the experiment branch, but my master is still back here. And that's a normal kind of situation. Now, how we get this work that I've done here, how we get that onto the master branch, so to speak, we'll see how to do that in a while. So I just showed you the git checkout command there, and I'm telling you now that this allows you to switch attention from one branch to another. And so the command is just git checkout and the name of the branch. There aren't usually any other options available to you. What that command does is it changes head to point to a different branch path file name. But of course, we know what the significance of the head file is. That now means when you do a git status, it'll tell you, oh, you're on this branch now. And if you do a commit, the commit is going to affect the branch that you've mentioned here. it'll change that branch file. It'll change what commit object it's pointing at. The other thing that the git checkout does is it completely overwrites your working directory. Now, of course, there's a caveat there. It won't actually work if you have some edits on your working directory. I'll come back to that in a second, but it does have that effect. If you're switching from one branch to another, it can, not only does it do this, but it will actually completely overwrite your working directory. So that's why I'm kind of putting the danger. It's not so much a danger signal as in you could lose stuff. It won't allow you to switch branches if you have some modifications made to files in your working directory and you have not committed them. It won't actually allow you to do a checkout or to switch branches. Oh yeah, so there is sometimes what you want to do is you want to create a new branch, but you also want to switch to that branch at the same time. And so you can do that actually with the git checkout. There is this -b option. So the effect of this is not to create a new branch, but also to make that new branch your current branch, i.e. get head to point at this new branch file that has just been created. So it's effectively these two commands combined. Another scenario, I do a git checkout of master, then the git branch command, what that does is it will list all of the branches in your repository. So because I've done a git checkout here to master, it'll list all the branches. That's the one I just created. The asterisk will always be beside what it considers to be the current branch, the one that you would commit to if you did do a commit. If I now go along and do this, so this is going to create branch X, and I'm also switching to that. So now when I do, okay, so I've created a new branch, and I've also switched head to be pointing at that branch. So then I go along and I create, I edit file A and file B, let's say, and I stage and commit. I then switch back to my master branch. And I said that when you change to a different branch, Git will overwrite your working directory, which means that, for example, the edits that you made to file A and file B, they are now no longer visible in your working directory because the master branch didn't have them. If I switch back to branch X, then I will see in my working directory the edits that I had in file A and file B. So that is just reinforcing this idea that when you submit the git checkout command, your working directory is completely overwritten. And I'm okay, just by way of a scenario, I'm kind of proving that to you. I'll just pause for a second now in case I've confused you on that one. No, okay. And I've already mentioned this. Git actually prohibits you doing a checkout if you have modified files that you haven't committed on your working directory. And so I'm saying, okay, if I just explain what I'm saying down here, right? So if we go back to here, I am creating a new branch X, and I'm also switching to that branch. I'm making it the current branch. Then I go along and I edit file A and file B. I don't commit now, I just edit them and leave it at that. Supposing then I try to git checkout master, it won't actually allow me to switch back to the master branch. It'll tell me you have some modified files in your working directory and you have not committed them. What do you want to do effectively? You can undo the commits and you've got to tell Git that you're undoing, sorry, not undo the commits. You can undo the edits. But you've got to do that via Git, or you can commit the edits to the repository under branch X, of course, and then you can do your checkout. So you're never in danger of losing anything. You can also do something called stashing, which I won't cover, but you can read up on it yourself if you want to. Typically, what you would do when you try and do a checkout and it stops you because it's telling you you've got some modified files in your working directory, in most cases, what you will want to do is commit those changes to whatever branch you're currently on, and then switch over to the new branch that you want to switch over to, in this case, master. So what will happen then quite commonly is you could have lots of branches and they're all diverging away from one another. You know, they all have their own commits, but they don't have, they're not kind of merged together. So let's dream up a scenario where we have diverging branches. So I'm saying, supposing we have, after committing changes to our experimental branch, so we're sticking with the same little use case. After some commits to the master branch, we then check out to the experiment branch, we then check out the master branch, and we do modify some files on the master branch, even though I told you we shouldn't really be modifying or doing commits on the master, but let's just ignore that. And we commit those edits to the master branch. So visually, this is what we now have. We had a commit on the experiment branch. We then switched back to the master branch, which was pointing at this here. We did some edits and committed them, which meant we moved the master branch on to the new commit. And now this branch and this branch are diverging away from each other. Like, it's quite possible that there are edits associated with this commit to particular files, and the same files were edited associated with this commit. And we'll see later on how we can resolve that. But for now, we're just illustrating this idea of diverging branches. I might have more commits along this branch here, and later on I might do more commits along this branch here. So clearly the two branches are moving away from one another, or diverging. And again, as I say, that's a very common situation. The other thing, obviously, is that to notice here is that C3 here, commit 3, we would say is a common ancestor to both of my branches. Like if we work our way back, we work back to C3. So C3 is where we started to diverge. The two branches started to diverge away from one another. And typically what we want to do is to maybe merge the experiment and the master branch back together again. And more than likely what we want to do is merge the experiment branch into the master branch. Okay, so typically the work carried out on a branch is either added to the master or merged into the master, or possibly you may actually discard the branch entirely. You're not interested in the work that you did on it because it may have just been experimentation. But it's going to be one or the other. So I'm trying to put another scenario to illustrate this merging and what it looks like from a Git repository point of view. So the scenario is, it's a different scenario now, I think, from what I've been using up to now. So I've got customer recommends, let's say, a change or a new feature that they'd like you to add to a particular application. And let's supposing it's a web application, it doesn't really matter. So a new feature anyway needs to be developed for a particular application that we have already deployed to some customers. And so let's supposing this is the repository associated with that application. There's a number of commits already on it. The master is always referring to the version of the application that would have been deployed to customers for customer usage. Okay, that's always the kind of assumption. So in order to develop the new feature, obviously I should do that on a separate branch. I shouldn't do it on the master branch because it'll take some time to do development. So I create a new branch and I'm going to call it just feature X, and I do some commits on it. That's fine. Now let's suppose that in the middle of my development of this new feature, another customer reports a bug in the current version of the application that has been deployed. And when anybody reports a bug, then we clearly need to fix that as quickly as possible. So what we do is we create another branch for the bug fix. And we do some commits on that. And that bug fix branch is going to emanate from the master branch as well. So we branch off out here, do some commits, and clearly now we have our diverging branches, but we've got 3 branches now at play here. Now the bug fix branch, obviously we would give precedence to that, and we would try to fix it as quickly as possible, and also get that fix back into the master branch as quickly as possible. So I'm saying here that the bug fix work, let's supposing it's completed, but we must merge it into the master, because the master is what we do, what we would redeploy to the particular customers that have the application currently working for them. And the way we would do that from a Git point of view is, what we want to do is to merge the bug branch into the master. So the sequence is, you've got to first of all change your current branch to be the master branch, and this is the command to do the merge. So it looks pretty straightforward. Okay, Git will take care of carrying out that merge, although as we'll see, it's a pretty straightforward merge operation in this case. But that's the command anyway, the git merge command. And really, for this particular situation, the merge is actually very straightforward from Git's point of view. The master branch was pointing at this commit here. In order to do the merge, it simply moves the master pointer to this commit. Bug Y is also pointing at that commit, but that's fine. So now master is pointing at this. This is now part of my master branch, which goes back around here. So that's what constitutes a merge in this particular case. It's a simple movement of the master branch pointer. We refer to that type of merge as being a fast forward merge, as in it just moved the branch pointer forward to a new commit. Very simple operation from Git's point of view. So I'm just reading the slide here. So the last commit on the merging branch is directly upstream. Oh yeah. So a fast forward is performed when the branch that you want to merge into the master is simply, I'm saying, upstream of the master branch itself. So if I go back to the previous slide, I suppose, back to here. So I wanted to merge bug Y branch and master branch, but the bug Y commit was simply upstream, as we say, even if there were a number of other commits here, and this is the current position of the bug Y branch. Still, the bug Y branch commit, the most recent commit, is, as we say, just directly upstream from the master branch. So it's still a simple fast forward merge operation, or the merge is a simple fast forward movement of the master branch right up to where bug Y is pointing at. So that's all that's involved in merging for fast forwarding. But a lot of merging is not as simple as a fast forward, as we'll see in a moment. you don't tend to do it, but you could delete the bug.y branch file using this command here. But because a branch is, from a memory consumption point of view, a branch consumes little or no memory. You know, it's just a simple little file, text file with one line, one hash value inside it. So we don't tend to delete branches ever. We just leave them there. Now, this is where we are now. We still have our feature branch working away and our master is up here. I've just gotten rid of bug.y, but it could still be pointing at this. But all we're interested in now is this master branch and this feature branch. But, and let's assume that we do want to include this new feature in our deployed version of our application, i.e. we need to merge this feature branch back into the master branch. But it's quite likely now that it's certainly not going to be a fast forward. We can't just simply take this pointer here and point it down at this. That isn't going to work. Because if you think, let's supposing there are a number of commits along this stream here, and there are a number of commits along here, and the master is pointing at this, as I said, we can't just take the master and just point it at this commit that would be over here. Why can't we do that? Because it's very likely that there are edits made along this path here, or new files added, or existing files modified, that have been made along here. They're not reflected here. So if we simply took the master branch pointer and pointed it at the commit that was down here, then we've suddenly lost all of the edits that were done along here, which in our case was the bug fix. So our bug is reintroduced back into the application. And just to clarify now that all of the edits that we did here was related to bug fixing. If we simply move the master branch pointer down to here to point to the commit here, there's no bug fixing code along here. There's no bug fixing code along here. So we've certainly lost the bug fix code. So that's fast forward or simple shifting of the master branch pointer won't suffice as a merge. It needs to be something a little bit more involved or intricate than that. So this is a very common scenario. So we still have this benefit of having a common ancestor between the two branches that you want to merge. In our case, it happens to be C3. So what am I saying on the next slide? C3 is a common ancestor, that's okay. The way we perform the merge is the exact same as before. So we check out the master. You always check out the branch that you want to merge into, which in our case is always the master, and you do a git merge of the branch that you want to merge into the master. So that looks exactly the same as before, but in this case, git is going to come back and tell you that you have some conflicts in the two branches that you're trying to merge. A conflict means that both of the branches that you're trying to merge have made edits to the same file and possibly in the same general location within that file. Clearly, Git has no understanding of the contents of the file. It doesn't understand code, but it will do a text comparison of two files to see where are the conflicts, and it will tell you where they are. It's up to you then to resolve them though. So when we try and do a merge of branches where there are conflicts between the two branches, then it will actually tell you where the conflicts are. And if you do a git status straight after, you get this kind of response back from a git merge. If you do a git status, then what you will see is stuff like this. It'll tell you that both branches have modified a particular file, and it will list that for every file where there are edits made by both branches to that particular file. So it's telling you which files contain the conflicts. If you look inside the actual file, note now this is in our working directory now that we see this. If you actually look inside those particular files, then what you look for are these markers here. And it sticks those into the file, telling you where the areas of conflict are. And we will see this the next day in the lab. And that's as far as it takes it. That's as far as Git can help you with resolving the issues. It tells you where the conflicts are. You've got to then work out, well, what should we actually do to this part of the file? And that may mean collaborating or discussing it with the other people on the team. And once you have fixed the conflicts, you have to physically remove these markers from the file. And then you can kind of complete the merge, as we say. So the what next is, okay, I've opened up the files that contain the conflicts. And so, as I said, you discuss with your team members as to how we can resolve the conflicts. The conflict simply will be that two people or more may have made edits to the same general area of a file. And we just fix that. So we edit the conflict files and fix the conflict areas. We remove the conflict markers, as I said. And then we stage using the git add command. We stage the current status. We stage the modified files in the working directory, and we do a commit, just as before. When you do that commit, this is really what you finish up with. We've kind of completed the merge of our feature X branch and our master branch. So we've got a new commit. What's unique, what's different about this commit in comparison to all of the other commits that we've seen so far is that this commit will have two parent or preceding commits. All of the other commits so far, like C3 only had one parent, C6 only had one parent, and so on for these down here. But C7 over here has two parents. And that's normal when you are doing a merge of two branches where there were conflicts in the branches that were being merged. And as I keep repeating, you will see this happening in next week's lab. So it's a lot of theory today, admittedly. So overall, the kind of the workflow that a developer goes through on a day-to-day basis is this branch edit merge workflow, as opposed to the workflow that we practiced, is it 2 weeks ago now, which was the edit commit workflow, edit stage commit, as opposed to speaking. Now we follow this kind of branch edit commit. In other words, when you're about to start doing some development work, the very first thing you do is create a new branch off of the master, do your editing work, and then merge that branch back into the master. You start off on another new task. First thing you do is create a branch off of the master, do your work, merge it back into the master, and on it goes. So no matter what you're working on, that's always the kind of the workflow. When you're on a branch, when you create those new branches, we kind of generally refer to them as development branches. And when you're on a development branch, well, you know that any commits that you do won't affect the master, which is good. So, you may find this kind of scenario happening. So you've created a new branch for this feature that you're developing. Let's say you do a commit on it. You think you've finished the feature, but suddenly you've found a bug. So obviously you've got to fix that bug and you commit the fix of the bug. Or in this case, I'm saying I forgot to include a particular feature. I commit it. I think I've done some testing down here. Then I find a bug. So I fix the bug and I commit that work. I do some more testing. I find that the bug fix actually isn't complete. So I need to do some more work. And I do this commit. Now, if at this stage now, all of these commits are on my my development branch, my feature X branch. And, some of these commit messages aren't great, really, okay, they're informative, all right, but really when we merge this branch back into the master, all we'd like to see on the master branch is a single commit stating that feature X has been added to the application. We don't need to know the background to, the process that you went through in order to get a completed feature X working. So we don't really want to see these kind of commits here on the master branch, ideally. But they would finish up on the master branch if we simply did a straightforward merge at this stage here. So what you can do is you can squash all of these commits into one commit and give that one commit a more appropriate commit message for the master branch. So how do we do squashing? Sorry, did I miss it? Oh yeah, this is how we would do squashing. So again, I'm repeating this sequence here. Here's the command. I know now at this stage, my feature, I know at this stage here that my feature is working. There are no bugs in it, and it's ready now to be merged back into the master. But I won't do a merge straight away. The first thing I do is submit this command here. And effectively what that does is it rolls back the repository back to here. But all of the edits that you were doing here are still in your working directory. So it's as if you never made these commits at all, but all the work that you were doing is still in your working directory. That's kind of the effect of this. And the ~4 here is referring to the number of commits that you want to kind of remove from the repository. 1, 2, 3, 4. That's where the 4 comes from. So that's what that command does. And then I can do a stage and a commit, and I give it a nice clean commit message. And then I can do a merge into the master. And now all that's going to appear on the master branch for all of the work that I did up here is this single commit message. I have squashed these commit messages into one commit message in order to keep my master branch commit messages clean and informative. When you're working on a development branch, maybe you want to commit the work that you've done so far, but you don't have necessarily, you're not really interested in giving it a meaningful commit message because you know you're going to do some further commits onto that branch and then do a squashing. So you can actually do a commit. And if you add this qualifier here, you don't actually have to specify any commit message. I'd avoid using that, to be honest with you, but it is possible. All I'm saying is up here is that sometimes when you do a commit and you have a commit message and you hit the return key and you didn't suddenly realize maybe the commit message isn't really that informative. Can I just undo that last commit message? Well, yes, you can. And that's how I'm showing you here how to do it. You can amend the last commit, but that's the only one you can amend. You can't go amending commit messages from way back earlier in the repository's history. And there are other little odds and ends commands that I'm showing you here, just a small subset of them really. If you want to find out what branches have you merged into the master, that's how you do it. If you want to find out what branches you have not merged into the master, that's how you do it. If you want to get more detailed information on a particular branch, the -v stands for verbose. That's how you do it. So there's just a whole series of commands that can be useful. To be honest, I don't use them that much, but you can imagine in a very large project where you may have 50 plus 100 branches, you may lose track of exactly which ones have and have not been merged into the master. So these can be useful for those kind of situations. Now, for once, I think I've timed it fairly well. That's the last slide on this set, and I don't intend to cover any more theory side of Git. There is obviously lots more, but so in next week's lab, we will practice using branching. Admittedly, now what you're going to be doing is creating multiple branches on your local Git repository and merging them. I said at the outset that the real use case for branches is when you have multiple people working on the same repository. In order to simulate that though in a lab, we would need to set up a GitHub account, get everybody, well, get groups of people committing and creating branches on that particular GitHub repository. And that's just a little bit more involved unnecessarily. In our case, we just need to get the basics of doing merging. But even using branching when you're working on your own on a project, using branches as a normal course of action is something that you should get into. Try and stop yourself from committing to the master branch directly. And it's just a habit really that you develop over time.